Thank you all so much for coming. When I had the idea for this event, I was like, is there going to be anybody in New York who wants to come to the intersection of browsers and WebAssembly? And clearly there is, so that's really exciting. So I'm Paul from JamSocket. We're here with a gracious host from SignalFire. I'll give the mic over to Ryan to say a few words. If that's okay to put you on the spot?
Yeah. Hey everyone, I'm Ryan. I'm an investor here at SignalFire, helping lead the majority of our early stage infrastructure investing. Thank you all for coming, and thank you for coming to our beautiful office. SignalFire is an early stage VC fund that's been around for about a decade now. We're investing in pre-seed, seed, Series A infrastructure companies across open source, developer tooling, data infrastructure, and cybersecurity. If you have any questions about anything infrastructure, please let me know. If you're starting a company, please let me know. If you just want to hang out and get free beer, pizza, please let me know. Yeah, thanks for coming.
Thanks for hosting. So we've got some exciting speakers tonight, so I'm not going to take up too much time leading into it, but I will take up some time leading into it. Because I do want to tell you a little bit about what we do and Browsertech in general. So Browsertech, by the way, is the event series, not the company. I'll get in the company in a sec. We started Browsertech events a couple of years ago. I guess it was 2022, early 2022, because we were all coming back from the pandemic at the time, if you remember back then. We're still doing vaccine checks at the door and everything. But we kind of realized that the web community that existed before the pandemic was not really the community we wanted to bring back. We were like, the web has evolved, the browser has evolved. There's people doing things like WebAssembly, WebGPU, WebGL, RTC, Web Transport, and they're not necessarily going to React events, or they're not necessarily learning about Gatsby and SEO and all the other things that are like part of web development writ large. So we wanted something that was for people exploring the fringes and the surface area of browsers with all this new technology. I sometimes like to say, like, if you're kind of reluctantly building for the browser because that's the platform people have and it's low friction, you're not like embracing hypertext, you're kind of the audience for these events. So we do these events, we do some dinners, we do a podcast and a newsletter. So you can find it all at Browsertech.com, and you can find links to all the other stuff. So please subscribe and follow and follow the newsletter. A bit about what we do. So the company is JamSocket behind Browsertech. We've been around about the same timeline in 2022. The gist of JamSocket is we realize that as people are building more and more in the browser, there's kind of some fundamental limits of the browser in terms of how much memory you can get and how much compute you can get. The ability to do interesting networking and all of that is just really restricted when you're just running in a Chrome tab. So we realized that the abstraction we wanted for a lot of these things was just to be able to spin up a remote process and kind of run some compute, connect to it from the browser, and when the user closes the tab, the process goes away. So sometimes I think of it as like AWS Lambda, but for WebSockets. I'm going to show you a real quick demo of this that will involve some WebAssembly. So first, I'd like to just show this demo because I think it is the demo that makes sense to web developers. We're like, okay, I get it. So this is me just starting a Jupyter notebook that I can interact with, I can run code. That code is running kind of on this remote server that I just started up in a matter of a second or two. And we gave it a host name. That host name is kind of universally tied to it. It's like a unique host name. And I can go and look at the performance in the dashboard and stuff. And when I close this tab, that process will go away. So it's kind of this way to start ephemeral processes. I promised this would have to do with WebAssembly, so I'm going to show you something else, one-handed. This is one of the things that actually I'll need a hand find here. That's wrong shortcut. Music. This is another example of how you can use these, is for sort of multiplayer backends where both of these are talking to the same ephemeral process. I go in and I can play. So the WebAssembly here is kind of cool. Both clients are running WebAssembly, and the server is running a separate WebAssembly module that contains substantially the same code. So the code for all of the rules of the game, the way that it changes state, are all embedded in WebAssembly on the client and server. And so when we send WebSocket messages, they're just little messages that sort of send the incremental update. And this is, I think, a really useful pattern that I want to talk about more in the future, but I do want to get into the talks. So I'll save that for another event. So our speakers tonight, and speakers, I realize I didn't tell you the order, so remember this order. So Carlo's going to be up first. Carlo Francisco is at Notion. You may have seen a blog post that he wrote 2 months-ish ago, I think, yeah, something, about how they're using, well, I won't spoil it, how they were using WASM at Notion. We have Kyle, up front. Kyle is at Development Seed and is prolific with a bunch of WebAssembly projects in Parquet world and geospatial. So yeah, looking forward to that. Andrew is at Prospective and is also the author of the Prospective, and is author of the Prospective library, which is data visualization all in WebAssembly. And Sean is at Renderlet, doing 3D in WebAssembly. So I'll hand it over to Carlo.
I'd rather just press the keys there, just so I'm not like,
Yeah.
Cool, thanks, appreciate it. Hey y'all, I'm excited to be here presenting at Browsertech. My name's Carlo. Today I'll be talking about how we use WASM at Notion, and specifically what I'm going to be talking about is how we brought something we're using in SQLite to the browser using WASM. And at Notion, we use this specifically to bring performance improvements that we were already running on our desktop app and on our mobile native app to the browser. So I'm going to tell this as a form of story because there's a lot of ways this kind of went wrong in the beginning, and I'll kind of walk through some of that. But first, who am I? I've been at Notion for 2 years. I'm on a team called Web Infrastructure, which works on projects like the one I'm about to talk about. We're sort of like a client infrastructure team. We work on like these bits and pieces that the product teams build on. And I've had various front-end roles before Notion. Most recently, I spent a few years at Datadog. I know there are a few Datadogs out here right now, working on the client-side app there as well. But Notion is the first place where I've been working more on the client infrastructure side of things. So before I kind of get into how we actually used WASM, I'm going to just give a very, very quick course on how Notion's data is architected. But first, let me just get a sense of, could you raise your hand if you've heard of Notion? And keep your hand up if you use it at your work right now. Awesome, that's amazing. Okay, so as you know, since you used it, it's an editor, or it has an editor, and it's what we call a block-based editor. And every new paragraph is represented with what we call a block. And every block actually is a row in our database in the server. So a block can be, a paragraph of text. It can also be something else like a to-do list or maybe a YouTube embed. And when you visit a page in Notion, you download all the blocks that are children of the page that you're on. A page is actually also a kind of block. When you edit any of the text on your page, we sync that up to the server. You get the idea. But as you might imagine, this doesn't always scale well, especially if you're on a page with thousands and thousands of blocks. If you all use Notion, I'm sure you've hit pages where, or maybe databases, in Notion that take a while to load. So for this reason, 2 years ago, or more than 2 years ago, before I joined, the folks working there introduced what's called the record cache. And the record cache, so I said in the last slide that each block has one row in the server-side database. This is in Postgres, by the way. To build this cache, what they did was to simply save the same database schema that's in that server-side Postgres database onto the local device. This was actually the native Electron desktop app, and we have native client apps for Android and iOS as well. So every time we save to the server, we would save to this record cache. Simple, at least in theory. So since these are running natively in Node in Electron's case, or in Swift in the iOS apps case, for example, this lets us run the SQLite libraries for those platforms. Hence, this record cache was implemented on the desktop and mobile native apps only. The cool thing is, when they first rolled this out, we actually saw improvements to our page load time of something like 50%, which is incredible. We track how long it takes for a page to first load and how long it takes to click to another page, and those all improved. But that's not the subject of this talk, strictly speaking. What we really wanted to do this year was implement this on browsers, and I had a huge advantage in that much of this logic was already written for these platforms, and actual SQL queries had already been written. So what I really had to do was get it working on a browser, kind of build an adapter for that. So what was our first pass? We set out to build a proof of concept using the official SQLite library running on WasM on browsers. This was made available in an NPM package sometime last year. So it has a bunch of choices for persistence layer. You could store everything in memory. Probably don't want to do that if you're trying to cache something, right? So this library had the option to use the OPFS, Origin Private File System, as a way to write the database file. If you want to use SQLite via OPFS, though, you have to do it in a web worker, which I'm sure many folks in this audience have used for various other features. But if you haven't written code in a web worker before, it's very simple conceptually. It's just code that's running in a background thread, isolated from your main thread's code. So for our first pass, we kind of just went with all these recommended options and plugged these technologies together to the existing caching code. And when we turned this approach on to a small amount of users, we found that it actually worked. We saw some modest improvements to page load for those users. But we quickly discovered some pretty big problems. And the first was something called cross-origin isolation. So SQLite via OPFS requires that your site is what's called cross-origin isolated. This involves setting a few security headers that limit what scripts can be loaded and limit certain features if they can't use those headers. It's actually really hard to pull off for most sites that have actual traffic. It's easy enough to set headers on all the pages you control, but your cross-origin resources have to set another header, and all cross-origin iframes need another attribute. You might see where I'm going with this, but raise your hand if you work on any sort of web application and you have any third-party scripts on that web application. Okay, handful of people. If you want your site to be fully cross-origin isolated, you have to go around and ask each of the vendors of those scripts to set the new header. They probably have to run it by their security team. They'll probably say, no, we don't have this in our roadmap at this time, right? But you might point out, if this was so hard to do, if you couldn't do this, then how did I turn it on, like I said in the last slide? Well, we were somewhat saved by what's called an origin trial for shared array buffer. So shared array buffer is the feature that enables this. Chrome lets you opt into these domain-based trials that temporarily bypass certain requirements, like cross-origin isolation. So we were actually able to turn this feature on just in a small percentage of Chrome traffic, but not in other browsers like Safari. That was enough to gather some performance data for this first pass. So that's what we did. Okay, second big problem is that we ran into SQLite corruption. So this is a pretty bad one. The SQL database basically got corrupt. We found in our logs that whenever we would try to save to the cache, some small percentage of the time, it would throw an error saying SQLite database was corrupt. It looked like this was actually happening on our desktop app too, and we didn't actually change the implementation of that. But it was happening at a much higher rate on this new browser implementation. It was pretty visible in our metrics. So this kind of stumped us because, we weren't doing anything that special. We were using the official SQLite library. We thought all of our queries were fairly robust after years of testing and production. So we thought about what was unique about the browser implementation. And we thought about how, for browser, people usually have multiple tabs open at the same time. So for each of those tabs, you'll have one dedicated web worker that then opens a connection to that single SQLite file in the origin private file system. So there's a little frowny face you might not see over here, but it's saying multiple open DB connections to the same DB. So this is different from our Electron app, where, yeah, you have multiple tabs in our Electron app, but they're talking to one single node process, the Electron process, and that's what's writing to the DB. This one's kind of doing this thing where multiple tabs are opening, may all be writing to the same file at the same time. And OPFS as a technology doesn't give you any built-in guarantees when it comes to concurrency handling. The concurrency story of OPFS is kind of bad. So we thought, could this be the cause of a lot of our issues? We tried to validate it quickly by applying a few band-aids. Like, okay, what if we did this super hacky thing where only the in-focus tab can actually use this cache? And tweaks like this, we found, did lower the rate of corruption. So we thought, okay, where there's smoke, there's fire. Maybe this is the thing that's actually the reason why we're seeing all of this. So at the same time, well, one more thing I'll say about this. So I think the obvious solution here was, let's make it work like the Electron app. Let's say only one tab can write to SQLite at a time, but all the operations from all the tabs have to be written at some point, but they should go through one DB connection only. So we thought, okay, that's our goal. That's how we productionize this. At the same time that we were investigating that, we noticed there's another way you can use WASM SQLite. It's WASM SQLite. It's the official library, but there's multiple sort of storage options you can use for it. And this is called the OPFS Sync Access Handle Pool VFS, which is kind of a mouthful. This is slightly different implementation. It still uses OPFS, but it uses a different strategy for actually saving the file structure with different trade-offs, which I will go through in this next slide. There's really one big trade-off here, which is where the regular OPFS variant requires cross-origin isolation, SAH pool, Sync Access Handle Pool, doesn't, which is kind of cool, right? But SAH pool has this other limitation that the regular one doesn't, by which it can only run in one tab at a time. If you try to initialize it in a second web worker, it'll throw an error. But remember, we concluded as part of the other thing we were investigating that we actually want to figure out a way to only run in one tab at a time. And that's how we're going to address the corruption issues. So if we figure out how to respect the queries in all the tabs, but route them through one tab, we can use this SAH pool thing and turn this on in all browsers. We don't care about cross-origin isolation, at least for now, with no corruption issues, which kind of solves both of our big problems. So we ended up accomplishing this by building a little bit more infrastructure, and I'll kind of walk through what's going on here. So in this new approach, you'll notice that each tab still has its own dedicated web worker that can write to SQLite. But we enforce a new constraint where only one of these tabs is actually writing to SQLite. You see the blue one there says active web worker. That's because that browser tab was elected to be the one that's actually writing to SQLite. So you might ask, how do we enforce this? We use another technology, which is a shared worker, which is kind of web worker's cousin. It's kind of like a singleton, if you haven't used it, that is shared by all the tabs. But it can't do certain things. But it can do this thing like orchestrating which tab is the active web worker. So it's acting as the orchestrator that's saying, this browser tab is active. No, actually, this one is. So let's say you have these 3 tabs in this illustration. If I close this one, the shared worker will detect that. And how it detects it is also a kind of interesting engineering problem, which I can get into later. But it detects that and then elects the next tab as the active tab. So this way it ensures that there's always an active tab. And then let's say that browser tab number 3 over here wants to execute a query. In this case, the tab sends the query over to shared worker. Shared worker knows which tab's active. It sends it to that, and then it executes the query. The data goes all the way back to that original browser tab. So that's the way that we enforce that there's only one tab writing to SQLite at a time. It kind of just works like our mobile native and Electron implementation, just with this shared worker thing. So you might ask, how did this actually work out? We built this approach. We turned on to real traffic. It did work. Not as dramatic, I would say, as when we turned this on for desktop users. And I'll say a bit about why. But our page load was still up. Page load was especially sped up, as you might imagine, for countries that have very slow API request times, since that's what you'd expect from a local cache. The other outcome was that we didn't see an elevated rate of corruption. There's still some, but it's comparable to the desktop app. And that gave us enough confidence to roll it out further. Now, why didn't we get the 50% improvement? It's kind of a bit nuanced, but basically, this cache doesn't benefit the initial page load as much. Because if any of you has profiled the initial page load of your app, you know that a lot happens, right? You download all the JavaScript, you execute all the JavaScript, you may set up certain things, you may make certain API calls. For browser, part of that is booting up SQLite and connecting to the SQLite DB. So that kind of happens concurrently with all the other stuff. So usually, just fetching from the API is faster, and it doesn't really benefit to add the SQLite record cache at the beginning, because it takes a while to boot up. On desktop or mobile native, it's always running in the background. When you open a new tab, SQLite's already available, but that's not the case for browser. You kind of have to boot it up. And I want to close this out with a few important takeaways. So if you're using OPFS for anything, just know that it doesn't have graceful handling of concurrency. You should be aware of this and design around it. Maybe write to different files depending on which tab you're in, or do something like what we did and make sure only one thing is writing to one file at a time. Web workers and shared workers and their cousin that many of you have undoubtedly used, the service worker, have different capabilities. It can be useful to combine them if necessary. And then, as of this year, fully implementing cross-origin isolation on a sophisticated web app is not easy, especially if you use third-party scripts. And this is kind of a bummer, because there are other features that cross-origin isolation should unlock, but it's just not the case yet. Okay, super quick plug for Notion before I close this out. We're hiring for IC and management roles. Talk to me if you're curious, you know the rest. And that's it. Thank you so much.
Thank you, Carlo.
Thank you, Carlo.
Yeah, you can what we'll do, we usually do, especially when we've got this many speakers, is like, hopefully the speakers will be around at the end, and so you can find them one-on-one. So Kyle, I've got this lapel mic for the live stream. It's a magnet system there.
Oh, interesting. So, does that work?
Looks good. And I'll just hand this over to you.
Is this already? Oh no, I gave away my.
And if you want to use the clicker, I just throw that in.
Sure. Yeah. Awesome. Hi. Thanks for having me. My name is Kyle Barron. I work at Development Seed. We are an open source geospatial consultancy, and I'll be talking about how I use WebAssembly and some of my open source projects that I build. So a couple years ago, in early 2022, I wanted to learn something new and decided to learn Rust, and especially Rust for applications for WebAssembly and Python. I've been working with analytic data and Arrow and Parquet file formats for quite a while, and so I wanted to have some way to use Parquet data in the browser. Parquet is a really compressed file format, and so it's nice to be able to get all of a lot of data into the browser in a really efficient manner. But Parquet is a really complex file format. It has a lot of different encodings, a lot of different compressions available, and so the implementations in pure JavaScript that had been attempted before were never stable. And so there was already a Rust stable Parquet implementation because Parquet had been, Rust is used for a lot of databases. And so I figured it must be possible to get this in WebAssembly. And it actually only took a few weeks around the holidays of 2022. It was pretty ugly, the code itself, but it was functional and actually pretty fast. And so this was some of the strengths of WebAssembly, to reuse an existing library that you could have implemented in pure JavaScript, but it would have taken a lot of engineering time. And out of the box, it's really efficient in Rust because it's decoding to this efficient memory format, Apache Arrow, and WebAssembly is really good on working with binary buffers. Now, we've loaded this data into this Apache Arrow tabular data format in memory, but what we actually want is to have this data in JavaScript. But so far, we've put a lot of work into getting the data into WebAssembly. And it's non-trivial to get the data from WebAssembly out actually into JavaScript. And so we might have some tabular data where we have maybe some numeric string. Arrow and Parquet can represent nested columns like lists and maps. And so how do we handle moving this data from WebAssembly into JavaScript? Well, the default way to do this is, the easiest way is to use some other serialization to move data from WebAssembly into JavaScript. And so the easiest way is this Arrow IPC format, which is some encoding that wraps all of this Arrow data. But to do this, we have to encode this data in the WebAssembly context into a single buffer, and then copy that massive buffer into JavaScript memory. And then Arrow's JavaScript implementation can parse that buffer into its table concept. But this is so much overhead when we put in all this work to get it into WebAssembly. Is there some way to do this in a more efficient way that isn't with two full memory copies? And so it's actually possible where the WebAssembly boundary is not totally opaque. You can read from JavaScript into WebAssembly memory, and you just can't read from WebAssembly into JavaScript memory because WebAssembly is sandboxed. And so here we come into a nice thing about this Arrow memory format, where Arrow is language independent, and so that means that the JavaScript implementation of Arrow is exactly the same as every other implementation. And so whatever you're using in WebAssembly, whether that be the Rust or C++ implementation, has the exact same memory layout as what JavaScript expects. And so I created this library a couple years ago to be able to do this without having this memory overhead, where you're able to create JavaScript table objects to have JavaScript tabular data without having any data overhead, any data copies from WebAssembly. And so that means that you can view these JavaScript tables directly from WebAssembly, where there's some pros and cons to whether you still want to copy, which is still more efficient than this other serialization because it can be copied directly instead of having to go through some other format. But when you're viewing, you have to be careful that the data in WebAssembly is still valid. It means that if you delete that data in WebAssembly, your table in JavaScript is now looking at invalid memory and is not what you want. But this also means that if you are working with some data in WebAssembly, every time you update that data, you will get the latest version automatically in JavaScript because there's no copying going on. There's also an interactive blog post that if you're interested more in how this works under the hood, that's pretty easy to find on Google. So this brings me to this larger project that uses some of these underlying components to make something fast for end users. And so I do a lot of work with geospatial data, and here this is a open source project called lonboard that makes it easy to visualize a lot of geospatial data from Python in a very fast way. And so here this is an example of visualizing 3 million points from Python in a few seconds, where each one of those has a different color, a different radius, based on some attributes. And there's a few different existing libraries, IPyLeaflet and PyDeck, that already existed for rendering geospatial data in Python. But IPyLeaflet has a lot of overhead because the leaflet library is not particularly fast. But even PyDeck, which uses DeckGL, a GPU-accelerated renderer, is not particularly fast because it uses a JSON encoding to go from Python over the network into the browser and then render from JSON. Whereas lonboard is much faster because it uses a binary encoding from Python into the browser. And so here, the axis actually keeps going. If you try and render more than 100,000 rows with IPyLeaflet, it'll crash your browser. Whereas lonboard can render as much as your GPU can handle. That is totally not CPU bound, that the GPU accelerated library is good as long as you can get data to it fast enough, and using binary data is what makes that possible. And so here, this is using Arrow and Parquet, the entire length of the process. And so this is enabled by WebAssembly because it's able to parse that Parquet efficiently and reliably in WebAssembly on the JavaScript side once the data has gone from Python into the browser, and then efficiently get that data from WebAssembly into JavaScript into the GPU. But up to that point, Python usually is running in a server environment either on the same machine or in the cloud. But it's also possible to get Python itself running inside WebAssembly. And so here, let me start running some cells so that these can run. Some of them take a little bit of time. And so here, this looks like Jupyter, which you might be familiar with if you've worked with Python. And usually Jupyter is connected to some remote session. But here, this Python is actually running inside WebAssembly in the browser. And so this is using a few different libraries. Here, this is loading data, Parquet data directly from AWS. Here, for demo purposes, this is a local file that I had previously downloaded. This is using the same Rust library compiled to Emscriptum for use in Python that is also used in parquet-wasm on the JavaScript side. This is loading this data file, which is open data from Ookla, the speedtest.net people who have collected data based on download speeds around the world. And then we can get to this point, and in a few seconds, this is a little bit slower than desktop Python because it's single-threaded for one, and WebAssembly is a little bit slower than outside of WebAssembly. But here we are able to render these 3 million points, where we can get full rendering capabilities. And with lonboard and the GPU, this is able to do some GPU-based filtering. So here, this is based on the range of download speeds that I want to visualize. This changes which points are actually rendered to the screen. There's still some future work here. You noticed when I went to render that data that it still took a couple seconds because it was encoding all of that data from Arrow in Python to Parquet buffers to copy into JavaScript to parse from Parquet into Arrow. But you saw before that we don't have to do all these copies to get Arrow data from WebAssembly into JavaScript. And so something I just got the prototype working today is actually being able to read Python's Arrow data into JavaScript without any copies. Because Python has its own implementation of Arrow that is also exactly the same as what JavaScript expects. And so we can look into Python's WebAssembly memory space and access that data directly into JavaScript without any copies at all. And so that is the future work for the next few months. And that's it. Thank you.
Thank you, Kyle. Andrew, we'll pass the lapel mic to you.
Hey, sir. Good talk, man.
And you want to plug in for the clicker?
No, I don't need
No clicker.
But I will plug in. What do I just AirPod in?
Yeah, just AirPlay.
Main, right?
The top one. Oh yeah, code. 4636.
Nobody steal that. Did that not work? 4636. Oh, it's connecting. Sorry, I'm an idiot. It's connecting.
Both Kyle and Andrew have been on the Browsertech podcast. So if you like the previous talk or next talk, you can listen to me talk to them on your headphones at the gym.
Does this thing work?
That does work, yeah. That's not video though. That's just
Oh.
that's just the. Do it. Something coming up now.
No, it's not.
Do you wanna switch order? Should we take a minute to debug
Yeah,
this?
probably.
Okay, Sean, are you ready? Oh yeah. We're gonna switch order a little bit. We can do that. We'll work on. So really putting you on the spot. So I'll need to grab the. I just grab the lapel mic.
Oh, that was a bad idea.
There we go.
Thank you.
This is for the live stream. And just it's magnet, so you can piece of right there. Thanks for the being up for the impromptu switcher.
I am happy to not have to wait for it any longer.
Is
that backwards?
Yep. The light goes up top.
Okay. We're engineers. We can figure this out, right?
Exactly.
There we go.
All right, and you can just twist it so that the.
Perfect.
Thank you.
All right. Cool.
You're on the right
Hi.
Wi-Fi, right?
I'm Sean. I'm the founder of a company called Renderlet, and we're going to talk today a little bit about how WASM is enabling us to build something we call GPU components. Does that work? Amazing. Yes. So WASM is coming soon to a browser near you. I joke because if you saw the call to action for this session today, we discussed that WASM is coming to the server or coming to the browser from the server side from all these hot popular startups. But why is WASM so popular in the space and as a compute technology? A lot of reasons for this. I posit that it is because it is the highest performance way to run safe cross-platform code. So obviously there's cross-cutting concerns. This makes sense in a web browser context. You've got isolated tabs. This makes sense maybe in a server-side context, but there's other virtualization technologies as well, like Docker or even on the front ends, like Electron frameworks. But WASM is a high-performance way to access your device's capabilities when you're in this environment. So I want to give a couple of architectural examples real quick. So like the old way of doing this, let's say, is bringing native apps into a web browser. And an example of that, I used to work at Adobe for many years, and here you can see a version of Adobe Photoshop. Most people don't know this. I love talking about this. That runs fully in your web browser. This is the native app. This is the native app compiled to WebAssembly through Emscripten, but bringing that entire power into your browser. more modern architecture, might we say, is the WasM engine, which Paul talked about in the Browsertech Digest newsletter very recently. This is where you've got kind of like a JavaScript front end, and like many of these web apps, you're communicating with the back end that's ultimately written in WebAssembly. So let's see an example of that. This is another Adobe product. This is called Project Neo. This is a neat little beta tool that's used to build 3D content using something called SDF. So it's an SDF-based modeling tool. You can see we can animate this little guy, move him around, and it looks pretty cool. But this is an example of the architecture. It's a fully web-native experience, but communicating directly with WebAssembly that's running the GPU engine in the background. Challenge is if I want to use this content, my options right now are to like download it as an image or maybe as a video and something that just works offline. What if we want to embed this 3D content inside our app and actually be able to interact with it in 3D in the design space? And so that's what I'm going to be talking about today, is what I like to call, that comes back, component-based architecture using WebAssembly. So to set the stage for this, we're going to talk a little bit about game development. My clicker not working? It's fine. Okay, so this is a scene from an excellent talk by Andrew Price, talking about the cost to build a video game. This is a scene from the Tom Clancy game. It's actually escaping me at the moment, but you can see that the cost to build this content is extremely expensive. And if your average, let's say 3D artist, is operating at maybe $60 an hour, why is this so expensive? Well, it's because you have to make these assets not once, but every time look good within every engine, every scene, every rendering context. If we're to look at how 3D content is made today, we're going to take you through a contrived example. We've got an artist over here who's been tasked with building an animated disco ball. So maybe they need access to an engine to draw a sphere on a screen. And so you've got an engine dev back here, a programmer who's probably working in C++ or something, that is giving them access to geometry functions, procedural geometry functions within that engine. That's great, but it needs to animate. And so maybe it's going to animate to run a fast Fourier transform on an MP3 file and use that frequency to modulate this. So the engine dev has to go and plumb this through the engine and get that somehow back as a parameter in the content creation tool. You can see the faces are getting a little less happy, right? It looks weird. It doesn't look right. It doesn't look the same in my tool that it does in my app. And well, okay, I guess we're going to hack the shader together, two different incompatible environments. And you see, it's just, it works. Like, don't get me wrong, this is a $40 billion industry, but it is kind of painful. This might remind you a little bit of some of the back and forth between maybe like UX design and dev when you're building UIs before we had some of these great tools like Figma or design systems that allowed us to use components. Here's how this should work. Our friendly programmer should build a component library that says, here's how you animate a sphere. And your artist should be able to plug that directly into their content creation tool and say, cool, it works. I'm going to drag and drop a couple lines to hook this up. And I've got my animated disco ball. So I'm going to give a greatly oversimplified view of GPU programming. I apologize if there's any graphics programmers in the audience. They'll probably find this offensive. But in order to build up towards a technical solution that allows us to bring that GPU compute along to the content creation tools and where the graphics context makes sense. So on a GPU, you've got objects like buffers. This is, let's say, vertex data. This is your position buffer for all of your vertices for that sphere. You've got animation parameters. You're writing outputs, let's say, to the screen or to a deferred rendering context. You've got shaders, which are the actual code that runs on the GPU. So the point of a shader, it's a massively parallel program that is designed to do a lot of the same thing at the same time, like filling pixels on a screen, or even today, like training AI weights, for example. But then across that, you have what I like to call pipeline state. And this is going to configure the GPU to say, this buffer plugs into the shader. And this shader is writing here. You're building your data flow diagram across the GPU of all these different things and configuring the runtime environment. You do this all through code on the CPU. So you communicate over a graphics API. Has anybody here heard of like DirectX or Metal or Vulkan, OpenGL? These ring a bell? That's typically how you do this. You issue instructions remotely to the GPU from the CPU side saying, go do this thing. So if we're building a technical solution, does WebGPU solve this problem out of the box? Who here has heard of WebGPU? Awesome. Who has used WebGPU? Yeah, that's a challenge. It's getting there, right? So it is a modern GPU API that runs in a browser. It's inherently cross-platform because it is part of the web. It's part of the web architecture, and your browser can implement it in all these different backends. It is very low level, and that's a good thing if you're writing raw graphics code because you need access to those functions. If you are a content creator, you probably do not want to know or need to know what the format of your vertex buffer is. There's also some issues with compatibility across GPUs because, for example, a mobile GPU, like something on your phone, might work, a tile-based deferred renderer might work very different from like your NVIDIA 4090 and your RGB gaming desktop that you have at home. And so WebGPU kind of has to modulate across these two different things. And it's a good API, don't get me wrong, but it is the wrong abstraction level for building a component-based rendering system where an artist might want to be able to hook up surfaces or hook up animation parameters or pass in transforms instead of operating with those lower level constructs. So Renderlet attempts to solve this problem. Renderlet provides a data-driven GPU interface directly to WebAssembly. So we take that graphics code, the CPU side code, we compile it to these WebAssembly components that are running in a WASM sandbox. And we provide this interface to the GPU across them. Developers can safely build pipelines out of reusable third-party modules, just like you'd grab components from a design system, for example, without having to write code specific to an engine or specific to an application. And so Renderlet kind of works at a higher level than these raw GPU constructs and allows us to build these arbitrary rendering graphs that's, at the end of the day, just data flow between WebAssembly modules. This is backed by some infrastructure that you may or may not be familiar with. WGPU is a Rust-based system for building some of those lower level constructs and talking to platform-specific GPU APIs. Actually, if you use Firefox, this is what they implement their WebGPU backend in. On the host side, we can either run in a browser context or outside of a browser context, but still in WebAssembly through WASI, or the WebAssembly System Interface. Mindy, who's sitting in the very back of the audience there, is the author of WASI WebGPU, which is the library that allows us to expose the WebGPU functions directly to out-of-browser WebAssembly. But then it's all on the back end, just those same familiar GPU APIs. So platform agnostic for the developer. I want to take us through a quick example because we're talking computer graphics. Let's see some computer graphics. This is a use case called procedural modeling. This is where instead of taking a static 3D asset, we are executing code at runtime like a lossless representation of that surface, much like the SDFs you saw in Adobe's Project Neo at the beginning of this talk. And we're able to take those and we're able to run those on the GPU inside any app at runtime without exporting our data. And that's kind of a two-step process. So obviously you're going to load in your content, you're going to generate your content. In this case, we're going to generate geometry procedurally. We're going to generate textures, we're going to upload them to the GPU. And then we're going to, at 60 frames per second, draw that into an existing scene, into an existing application. So, if I may. This is how we generate this data, for example. Here's a specification we use to build that graph of WebAssembly nodes that represents this building. And over here, you see that building running in a web-based context with some shading parameters that make sense for a web-based editor. If we were to go over here now, if I can actually get this to work, I'm running a Windows VM inside my Mac to make this app work. So bear with me here, this demo. We've got that same building, there's WebAssembly modules. I preloaded it because the internet's a little slow here, but we're rendering on top of Bing Maps here, for example, and we're showing those buildings parameterized by values that matter to this application. And just to show, these are not static 3D assets that only work on one content. We've varied the parameters, we've varied the colors. You could vary this based off of geographic data if you're importing building footprints, for example, from OpenStreetMap. It's integrated in, let me set this down. It's integrated in with the application's lighting engine directly, so you get the global illumination effects. The artist did not have to program for these specifically themselves. It all just kind of works out of the box. And similarly, I can, I'm going to load another module now. I just want to give an idea of the scale. I've loaded a few buildings there. But this is fast. Every one of those is generated using WebAssembly. And sorry, my keyboard was stuck there. Let's generate like a, I don't know, 50 by 50 grid. You see, there we're loading a ton of those. Those are all executing at runtime. It's running, it's loading, it's rendering. No application code required. We just exported a few variables for our lighting calculations in, and everything just flows through the data flow. Okay, let's go back over here. All right, so that was it. Just to summarize, through WebAssembly components, through this component-based architecture, we can take this same GPU code, we can run it in a browser, we can run it outside of a browser, we can run it inside any app, and it just kind of works through this component-based architecture where everything's connected via data. If you're interested in GPU technology, we are hiring. We are a pre-seed stage startup. If you want to come work on cool things, come find us, come talk to us. I've got excellent investors and the whole team's here. So thank you for your time.
Thank you, Sean.
And then I'll just get a hand that back to Andrew.
There you go. There you go.
So much.
And we're going to pray to the AV gods.
You have a kid. It's going again.
No. I'll try the restart real quick. Or maybe the Wi-Fi. There we go. 2958.
Hooray! You did it, America. Thank you so much. Does that work? Sweet. Hey everybody, I'm Andrew. Ooh, that's loud. I'm Andrew. I work at the Prospective company, which is a company that builds this, Perspective. Get it? Prospective, it's the professional version of... Yeah, nobody gets it, it's all right. We're not good at naming stuff. I apologize. Talks are hard to author, especially short talks. This might be actually a little bit shorter than all the other ones, which is especially bad because they were so good. I'm going to do it anyway. Let me give you a brief background of what Perspective is and why it's here. Perspective is a database and a spreadsheet merged into a widget that runs in your browser. It came from working at a large evil corporation that had some very large data problems and a ton of money to spend on computer science problems, but some really, really bad web experiences. And we were bored. We had a lot of C++ code lying around, and we decided to see if we could take what we had been building for desktop experiences for years and just deploy it on a browser and get a better user experience. And we did it, and we didn't. It was terrible. And then after years of development and benchmarking and testing and iterating, we came out with something that is quite fast, it can hold a lot of data, and is a cool overall experience. To give you an example, so this is our enterprise product. It's got a bunch of cool stuff on it, mainly some data sources. As a WebAssembly project, we take performance very seriously, which you can see because if you go to any of our release pages, you'll see at the top of our assets list a benchmark arrow, which Kyle was talking about a little bit earlier. The arrow part, not the benchmark part. And if I go over to our enterprise product, sorry, I'm gonna put this down for a sec. If I go over to enterprise product, I copy this URL, go back over here, paste it in the URL field, open this thing, click this button to use our special enterprise magic to bridge out of the browser. You can see that we get this nice little arrow file that has every version of Perspective that we've ever produced in a nice line chart showing every feature that we've ever built with every version, showing that Indeed, minus a few little bumps in the road, we pay a lot of attention to performance and make sure that it gets better with every release. You guys don't want to hear me talk about our enterprise product. I thought I'd do something fun. So I made this little game. I call this Let's Make a Deal WebAssembly Edition. Nobody likes that. How about Jeppersembly? Fuck it, we're going with the first one. Carlos, believe you already asked us, how many people in here do WebAssembly like as a job or use it professionally? A couple of y'all? Okay. Don't cheat. What I have here is a couple of JavaScript functions and a couple of functions written in Rust. They're compiled with just plain Rust C and using WASM bind gen to generate an easy API to call into, although that was not strictly necessary for this example. O3 optimization level, no WASM opt, no magic tricks, no SIMD, no multi-threading, no GPU. Just completely vanilla Rust versus JavaScript. The goal of this game is to guess which one of these is faster. If I intended to let y'all play along on your phones. Unfortunately, GitHub is being a pig today, and they've been building my website for 17 minutes. So I'll have to post the link later. But this is all running in my browser. It's not cheating or anything like that. All right, round one. What we have here on the left is a Fibonacci function. Simple recursive Fibonacci function, no memoization, and roughly the exact same function written in Rust. What's the default numeric type in JavaScript? What is a number type represented? Anybody know? Right. So on the Rust side, I made this in F64 to try to emulate exactly what JavaScript does, right? Show of hands, what's faster, JavaScript or WebAssembly? WebAssembly first. Who thinks WebAssembly is faster? That's not a trick. Or maybe it is, I don't know. So like 5 people, I think that means everybody says JavaScript, right? You're right, it's JavaScript. But let's take a look at exactly how much faster. So down here we have a little perspective. I'm going to make a table out of it. I'm going to open it up. I'm going to group it by test and split it by runtime. And I'm going to make it gradiated so you can see way in the back which one is faster. I'm also going to duplicate this table. I'm going to turn this one into a bar chart, and I'm going to move runtime over to here also so you can see it nice. Okay, cool. JavaScript's faster than WebAssembly. Why? Because you've been lied to. It's more complicated than that. Sorry, I actually should have prefaced this. Everything in this talk is a lie. Benchmarks are incredibly hard to get right. And it's 1,000 times worse in a browser or a managed language where you have a runtime or a compiler that is doing black magic while you're running your program in some cases. So this is more of a joke and to make you think about how the benchmarks of these things work rather than to make a claim that one of these is necessarily faster than the other. So let's try round 2. Same function on the JavaScript side. Recursive Fibonacci function, no memoization, except now we're using unsigned 32-bit integers on the WebAssembly side. Which one's faster? Who says WebAssembly? A little more confidence in WebAssembly than last time? I think that means that the crowd in general is pro-JavaScript, right? Let's try it. WebAssembly won this time, but you'll notice by like a fraction of a millisecond. By the way, I should tell you a little bit about the architecture of these benchmarks. We have 3 web workers running in this browser. One of them is the Prospective data engine that's powering the visualizations. One of them is the JavaScript runtime, and one of them is the WASM runtime. I broke them up just to make sure that nobody complained about it being unfair or stealing CPU from one processor or something like that. And also because I wanted to see the bars grow at the same time. I thought it would be a lot of fun. Y'all are only at 50% right now. I hope you don't work in this field. It was a joke. Okay, round 3. We've got a 10 million element array in JavaScript. How many people knew you could make an array of 10 million elements in JavaScript? You can. All this is doing is iterating through the array end to end and multiplying every number, or accumulating the total by multiplying it by every number. So all it's doing is reading out of the array and multiplying some stuff. Same thing over here, building a big array. I did a little Rust. Put the array in static scope to make sure we weren't measuring array construction time, but asterisk, this stuff is really hard to get right. Do you know what the black box function does in Rust? This is a transparent identity function that basically tells the compiler anything could happen in here, don't optimize it. Turns out the LLVM is really, really good at making functions constant when they don't do anything. I'm not going to tell you how much time I spent thinking like, wow, WASM is 0 milliseconds for every single time. Which one of these is faster? Iterating through 10 million elements in a JavaScript array and a vector. Who says JavaScript? Who says WebAssembly? Ooh, WebAssembly is a profound winner. Then you're all wrong, every single one of you. It's not a huge gap, but it's noticeable. Why? Anybody know? It's a rhetorical question. I actually don't. I mean, I have some. I could find out. I have some guesses. This is one of them. Same thing as before. We turn this into a data type that I know has faster multiplication. That is easier to put in an array. That should iterate faster, and that is something you can't necessarily control in JavaScript. JavaScript does have native integers, but you really have to bend yourself in a pretzel to make sure that every function you pass and everywhere you use them, they stay native integers. So just like for 10 million elements, JavaScript array versus a big old Rust vec, which one's faster? Who says WebAssembly? I think I shook your confidence on the last one, huh? I think that's JavaScript, right? JavaScript is the winner here? All right. JavaScript won this time, but again, like the difference is basically non-existent. And as I said earlier, benchmarking is very hard. I'll bet if I did this talk again, I might get a different number. Let's try something else. So same example as before, except now I'm not using a JavaScript array anymore. I'm using a uint32 array. uint32 array is a JavaScript type that allows you to get basically raw memory access from JavaScript. So this is memory layout virtually identical to what a box slice would be in Rust. U32s on the Rust side, in theory, float 64s on the JavaScript side, except very high probability these are actually being optimized into U32s at runtime. Which one of these is faster? Who says JavaScript? Okay, now who says WebAssembly? I feel like y'all are now evenly split. Have I shaken your core beliefs yet? I'm just gonna pick WebAssembly, but I'm not gonna hold y'all to this one. In this case, again, like, strangely, nothing happened here, basically. We went from an array in JavaScript, which is a linked list or an array-backed buffer or an array-backed buffer with even worse heap allocated objects depending on what you passed into it, versus what is unambiguously a packed array of uint32s, and nothing changed in the benchmarks whatsoever. To me, that says JavaScript in this is doing a really good job of making sure that the array that I used in the previous example is at runtime a uint32 array when it actually executes it. But only the Chrome developers know for sure. Apologize for the cursing in this example. This is a really big string being converted to base 64. This is the same really big string embedded in a Rust WebAssembly binary, also being encoded to base 64 with the base 64 crate. Base 64 encoding is a interesting encoding for benchmarking because you can predict exactly how much memory you need for the base 64 encoded string before you allocate anything, as opposed to like a zip file or something like that. So this should be very low heap allocation, but this isn't written in Ruby. There's a built-in browser native function, and it was written by presumably Google engineers who spent a lot of time playing benchmark golf. So which one of these is faster? 1,000 iterations of a big string in JavaScript or 1,000 iterations of transforming a big string in Rust? Who says JavaScript? A lot of JavaScript heads in here. WebAssembly? That's like tied though, right? That makes me really happy, by the way. I'm glad that I freaked you all out. So it turns out WebAssembly is quite a bit faster in this case. Sorry, what'd you say? No. Well, asterisk, benchmarking is really hard, and there's almost certainly a ton of bugs in here. But as far as I intended this to work, the exported function is what's getting benchmarked, not the fetch. So the fetch, since it's static and outside the body of the function, should be allocated at module import time, not at function test time, I think. But code's on GitHub. Feel free to call me out. We're hiring also. OK. If there's one thing that Chrome should absolutely do better than downloading my own JSON parser is to parse JSON from a string, right? This is built-in Chrome parse a string that is already in memory versus Serday. Everybody know what Serday is? Serialization format for Rust. Doing the same thing, it is parsing it into a type called JSON or Serday JSON value, which is an algebraic data type meant to roughly mimic the type of structures that are available in JSON. So not exactly an apples to apples comparison, but roughly intentionally the same, and I still think surprising. Who says WebAssembly? Who says JavaScript? I love this. This is great. JavaScript is quite a bit faster in this case. But when I wrote this, I was intending it to be the other direction. I intended to show that Rust was quite a bit faster, and it kind of got me thinking. I was like, huh, you know what everybody says about WebAssembly, or what I read constantly about WebAssembly is that the FFI, the boundary between your WebAssembly memory and the JavaScript heap allocation, is very frequently the source of a lot of slowdown that gets introduced into complex WebAssembly-based implementations because, as several other presenters said today, it's very difficult to read stuff from the JavaScript side into WebAssembly without copying it. So in this case, what I've done is I've explicitly moved the copying of the string from the JavaScript side into the benchmark function to make sure that we are allocating, every time we run this function, we're copying the string from JavaScript heap memory into WebAssembly, because WebAssembly, without being connected to JavaScript, can only make your computer warm. It can't read files, it can't get strings, it can't do anything. So you're eating that cost whether you like it or not when you're dealing with real WebAssembly implementations. Obviously, WebAssembly is going to be, WebAssembly is going to be even slower in this example, right? So yes, it is actually slower in this example, but honestly, the difference is so small as to be negligible. And having been working in WebAssembly for the better part of a decade at this point, the overhead that we frequently hear about being one of the big adoption issues in WebAssembly, this is something that gets dramatically better with every Chromium release, with every new iteration of the technology. It's not something that we at the Prospective company really even take into consideration anymore, except when we're doing these little micro benchmark games. And that's my talk. If you got a score of 7 or 8 out of 8, come talk to me. We're hiring. And I'm going to go fire myself. Thank you all.
Thank you, Andrew. I want to say thank you again to everybody involved. Thank you to SignalFire, our hosts. Thank you to our amazing speakers. My colleagues Taylor and Michael at the back have been helping with the event, and my colleague Felicia in San Francisco has been helping with the live stream. So we've got an amazing team that made this all come together, and I couldn't be happier. And thank you all for coming out. Again, I was not sure how big a WASM event could be. So very happy. We do plan to do more of these, not necessarily all around WASM, but around browser tech topics in general over the coming months in New York, and we take it on the road sometimes too. And so yeah, come talk to any of us about future browser tech stuff. Thanks.